So, uh, because we didn't really have a chance to go through them during the last few classes, I want to review some of the main topics that you learned about so that you'll be ready for the exam on Tuesday. Because again, the exam will be focused on only chapters 8 through 14, and it'll just be talking about the main takeaways from each of those chapters. So again, like I said, the exam will just be about 25 questions. So there will be about 4 questions per chapter. So about 4 from chapter 8, 4 from chapter 9, 4 from chapter 10, etc., etc. So that's what I'm basically going to be going through, just those main parts of these the last half of the book. Um, also, um, also, just so you know, so I never completely read through chapters 8 through 11, 8, 9, 10, 11. So when I started, it was 12, 13, and 14. But I think I got the gist of them. So hopefully, and the questions I put on here are not that hard. They're easy enough for me to understand, and I didn't even read the whole chapter. So again, don't worry about the exam. Just chill and but like I said, we will go through some of these basic takeaways from the chapters. So let's see how this goes. Okay. And basically, oh, this is what I was going to say. The other thing, pretty much this whole video should basically capture any answer you need for the exam. So I actually have the exam right here. So I will be looking at the questions and talking basically just about these questions as we go through. So just listen up and you should be good to go. Okay. So the first chapter, chapter 8, was talking about measurement and units. Um, so a few things that you guys would have touched on in this was probably stuff that you learned about probably in math back in your elementary school days. I remember learning about how many inches are in a foot, and then learning about meters and kilometers and all that stuff. So that's what this chapter was mostly focusing on, to give you guys the understanding of how scientists measure their different objects. So first of all, we all know that in America we use I call it the English system. I don't know if that's a technical name for it, but inches and feet and miles and ounces and all those different things that we are very familiar with and use on a daily basis as far as measurements. But the rest of the world, except for I believe 2 other countries, we're only one of the 3 that doesn't use this system. They use the SI system, which at first I was like, "What's the SI system? I've never heard of that." But apparently, we Americans just call it the metric system. So I got that finally. I was like, "Oh, okay, we're talking about the metric system." But SI system of international system of units, the international system of units. Okay, so this chapter it gives you the different international system units. There's 7 base units: the meter, the meter, the kilogram, the second, the ampere, the Kelvin, the candela, and the mole. You guys don't talk about it all, the candela or the mole. So it kind of briefs you on some of those base units and gives you the definition of the prefixes. The prefixes are like the deca, hecto, kilo, mega, giga, tera, peta, exa, zeta, and iota. You don't use most of those last ones. But the kilo, the mega, the centid, the milli, the micro, you guys use those. Those are the prefixes that would go in before the base unit. So you would have, a millimeter or a kilometer, excuse me, a centimeter, a millimeter, a micrometer. Okay, so any of those prefixes go on those base units, and that just tells you that you need to either multiply or fraction out. It does explain on how to do all that here. So again, in America, since we have that other system, the English system, it's actually not as logical or efficient to use as the metric system or the SI system because say you're going to measure, let me see, they give an example here. Say you're going to measure a liquid of some sort. Well, you could use several different names of measurement. You could use pints or quart or teaspoon or tablespoon or gallon, or there's just so many different ones, and they all are related to each other in different ways. You know, there's 4 quarts in a gallon. How many pints are in a gallon? Like 16 or something. And how many teaspoons are in a gallon? Like who knows that? Okay, so it's just kind of a jumble of different measurements. But with the SI system, the metric system, everything is very consistent. If you need to measure something, if you need to measure the distance of something, okay, instead of inches and foot and mile and all those that we have, and they don't equal up to each other very consistently, we have meter. Meter is the base unit for distance. So we could have the kilometer, the millimeter, the centimeter, the micrometer, okay? Those are all building off of that base unit of the meter. So that's why the SI system is actually technically more logical than the English system. Personally, I like the English system better just because that's what I grew up with. But I do understand where everybody comes from when they say that the SI system is more logical because it really is. All right, so let me just look at my notes over here. So just to brief over those prefixes, like we were saying, kilo, mega, centi, milli, micro. Okay, so the kilo is 1,000. So if you have kilometer, that's 1,000 meters. Mega is 1,000,000. Okay, so if you have a megameter, that's 1,000,000 meters. Centi means one 100. So if you have a centimeter, that's 1/100th of a meter. Okay, so you have a meter, you have a centimeter. Okay, there's 100 centimeters in a meter. If you have a millimeter, there's 1,000 of those in 1 meter. Okay, meter, millimeter, very tiny. Okay, and micrometer would be 1/1,000,000th. Okay, 1,000,000 micrometers in a meter. Okay, that's a lot. So you see how those prefixes work. Okay, keep a note. All right, and then let me see here. This is again, that was basically what we were learning about in chapter 8. So pretty much, like I said, back to kind of your elementary math days. And then converting, of course, they tell you how to do the unit conversions, but don't worry, we didn't do any of that on the exam. I did not really put any math on the exam. Okay, so I'm going to move on now to chapter 9. Okay, chapter 9 is property of substances. Okay, chapter 9. So property of substances. This is kind of getting into some chemistry, and it first talks about the physical properties, okay? So different things like hardness, malleability, strength, elasticity, okay? Different things that you can physically know about a particular substance. Part of that includes temperature, pressure, and volume. Now, just remember for temperature, the SI system, the metric system, of course, it has a separate way of measuring temperature than we usually do here in America or even in most of the world. Most of the world, I think, uses Celsius, right? We use Fahrenheit. The SI system unit for temperature, though, is the Kelvin, okay? So the Kelvin, and again, it explains it here in the chapter. So then the other property of substances that they talk about the phases of matter. Excuse me, one moment. This is another part of the physical property of substances, okay, the phases of matter. Again, I remember learning back probably in third grade that there's, liquid, liquid, solid, and gas. Okay. There's also a fourth phase of matter, which I did not know, called plasma. Okay, so there's actually four phases of matter: that plasma, solid, liquid, gas. Okay, and it explains the differences between each of them. Um, those aren't too hard to understand. It's, if you think about it, when they're talking about a solid, the particles are all pretty much in the same position. They don't move. The particles aren't moving around all much. You can actually see here in this, they give you that little picture of the particles are basically staying the same. They're attracted to each other and they stay together. When the temperature begins to heat up, they are able to move around a little bit more, and that's what this photo here is. You can see the particles are free moving a little bit more. Okay, so they're free to move. That would be the liquid stage. Okay, now the next stage, when they become a gas, they are going very, very fast because now they're really heated. So you can see they're pretty much, as he describes, going like billiard balls. Okay. So that is the gas stage. All right, so we will continue on here. Let's see where we're at. Okay, then, so again, I said there's different properties of substances. We just did the physical properties. Then we're moving on to chemical properties. Okay, this is another section. So the chemical properties, there's different chemical properties of substances. So some substances are flammable or combustible. Some substances oxidize or corrode. And then some substances are toxic. Of course, you all know what that means. And some substances are chemically stable and some are chemically unstable. So I'll just give you a few examples that they gave here of some substances and their chemical property. So wood is flammable, combustible, of course. Oxygen, that is what supports combustion. Okay, without oxygen, you can't have combustion or fire, right? Plastic is chemically stable. Okay, so if you throw this out in the backyard, you're not going to come back in 20 years and see that it's gone and degraded, okay, or decomposed rather. It'll still be there, okay. It is chemically stable. Its substance does not break down, maybe after a very, very, very long time, okay. Aluminum, that oxidizes to form aluminum oxide. Gold does not oxidize, okay. That could be why it's, I don't know if that's why, but it could be part of why it's so valued. You don't have to keep it clean to keep it from oxidizing. Gasoline is flammable, combusts, okay. Rattlesnake venom, toxic. Glass is not flammable, and it is chemically stable. So if you throw a piece of glass out in your backyard, you've probably found pieces of glass in your backyard, and they could be from 300 years ago, for all you know, because it's chemically stable. It's not breaking down. Okay. Chlorine is toxic. Don't ask why they put it in swimming pools. Hydrogen is flammable and combustible. Gunpowder explodes. Starch packing peanuts are chemically unstable. Okay, so apparently if you throw these out in your backyard after some time, they will, they are biodegradable, so they will decompose. So after a while, they will break down and they will no longer be starch packing peanuts. I'm trying to think of some other things that are chemically unstable. I guess anything really that breaks down. So, a banana peel, chemically unstable. Fabric is chemically unstable. After a while, it will break down. And so that list can go on forever. Dead animals are chemically unstable. They break down even if something wasn't to come eat them first. Okay, and then moving on, water, not flammable, chemically stable, non-toxic. Pretty much gotta love water. Sodium oxidizes to form sodium oxide, and paper is flammable or combust. So again, that list here, you see that? Okay, yep, that's the list I was just reading. Substances and their chemical properties. All right. So that brings us on to our next chapter, chapter 10, which is force and motion. Okay, so this is a little bit more what I think about when I think about physical science. Okay, so first of all, you talked about some famous scientists. Looks like well, we have Greek philosopher Aristotle, of course, Galileo Galilei, and then we have Sir Isaac Newton. And of course, he gives us the 3 laws of motion, which we will talk about in a moment. Okay. So then he goes over some basic things, some basic terms: velocity, acceleration. Okay, acceleration means changing velocity. Okay, so when you accelerate, you can either be going faster or slower. Sometimes we hear the word deceleration. If you're decelerating, you're slowing down. Okay, but in physical science, they say it's more common to just use the term acceleration. Okay, so acceleration doesn't mean speeding up. It just means a change in velocity. Okay, so you're not going the same speed. You're speeding up. You're slowing down. That's acceleration. Okay. All right. So more math in here. Okay, now Sir Isaac Newton's laws of motion. All right, we'll go over a few of these because these are just so fun. Okay, so we'll go over all 3 of them briefly. So the first law of motion: in the absence of a force, an object will remain in its present state of motion, either at rest or moving at a constant speed in the same direction. Okay, so this is pretty easy to understand, right? If you have, let's think, if you have a top spinning on a table, okay, it will keep spinning until eventually, of course, the friction from the table and the air resistance will slow it down and it'll finally come to a stop. But you can see that if there was nothing holding down, that top, there was no friction, there was no air resistance, it would keep going. Okay, sometimes they look like they can go forever. Or even think about the Earth in orbit. Okay, the Earth has been in orbit for however many years, probably millions of years, something like that. And it's not stopped. So it clearly doesn't have much acting on it to make it slow down. Okay, so unless there's an object, unless there's a force present, the object will continue in its state of motion. Okay, either or it'll continue to it'll either continue moving in the same speed, in the same direction, everything like that, or it will stay at rest. Okay, so like sometimes when I don't feel like, getting up in the morning, I stay in my bed, and unless somebody comes and drags me out of the bed, then I'm going to stay there. Okay, so that's kind of another part of that first law of motion. An object that is in rest will stay in rest unless acted upon by an outside force. Okay, outside force being my mom when I was younger. Not really. Okay, Newton's second law of motion. The acceleration of an object is proportional to the force acting on it. Okay, this one is the one that's a little bit trickier. Okay, because basically it's just an equation. Okay, that equation. Can you see that? Okay, great. A equals F divided by M, or acceleration equals force divided by mass. Okay, so just to basically explain what this is talking about, if you know, he gives the example of a car. If you know the mass of a car, you know the mass of the car and its acceleration, okay, how fast it's going, then you will be able to determine the force that is causing it to go that fast. Okay, or if you know the force and the acceleration, you'll be able to calculate the mass of the car. Or if you know the mass of the car and the force, you'll be able to tell how fast it's going. Okay, so this equation basically gives us the format for figuring out those different variables. Okay, so um, so that is something, I guess, that physics that scientists will use in physics quite often, that particular equation, because, well, you know, there's so many things in our day-to-day life that are affected by acceleration, mass, and force. Okay, even your own self probably walking across the room, you have a mass, you have an acceleration, and the force of your foot with the ground and the force of your strength moving you. Okay, that all is combined in this equation, so you can always calculate it. Again, don't worry, we're not doing any of those calculations on your exam, so just as long as you know the basic of what it means. Okay, and then the last law of motion. When one object pushes on another with a certain force, the second object pushes back on the first one with equal force. Okay, so here's an example of a guy playing baseball. Okay, you all have that picture, right, in your book. So you can see when he hits the ball with the bat, he is applying a certain amount of force on that ball. The ball is actually applying the same amount of force back on the bat. And he can tell this by the fact that when he hits the ball, he can feel that boom. That's that force of the ball hitting back. So it's equal. It may not seem equal because that ball goes flying, right? But the force of one object pushing against another object, this second object will always push back with an equal force, okay? It'll just probably manifest itself in a different way. So, let me see here. Okay, so Newton's third law also applies to objects that are not in motion. So a car sitting on the pavement exerts a downward force on the pavement and equal to the car's weight. The pavement will exert an equal and opposite upward force on the car, which holds the car up. Okay, so if we didn't have that equal force thing going on, things would not be how they are. Okay, so you know, this laptop sitting on my desk here is putting an equal amount of force on the desk as the desk is putting on it. So if this laptop is putting more force on the desk, well, the desk would be going down. Okay, so it's equal. All right. All right. Great. Moving on. Okay, great. Chapter 11. All right, this was another tricky one. This one is compounds and chemical reactions. Chapter 11. Okay, so compounds and chemical reactions. This is chemistry in our physical science book, but that's okay. All right. Hold on. Let me make sure I'm on target. Okay. All right, so the beginning of this chapter, they begin by explaining chemical equations, okay, which kind of look like this. Here's an example of a chemical equation. Okay. I'm not going to go through everything on there, but there's those letters and numbers mean different things, okay? So they represent, of course, different molecules or atoms. All right, and then when they're put together like that, they can show how different chemicals or different substances uh, combine or react with each other and different things like that. Okay, so then he goes on to explain what an ion is and what polyatomic ions are. Okay, so just to briefly go over that, an ion is an atom that has either gained or lost one or more electrons. Okay, so it's either gained or lost an electron, one or more electrons. So it is no longer after it's ionized, it is no longer have an equal amount of electrons and an equal amount of protons. Okay, it's either got more electrons or more protons. Okay, and that means it's either got a positive charge when there's more protons, or it's got a negative charge where there's more electrons. Okay? So a hydrogen atom is the most common ion because the only thing that makes up a hydrogen atom is one electron and one proton. So once one electron is gone, which I guess doesn't take much to do, it's ionized, okay? Because now it's just got one proton. And here's the little picture of a proton, ionized hydrogen atom, okay? Positive proton, one proton, electron is gone. Okay, and then a polyatomic ion. That's when you have many atoms. Polyatomic, yes, meaning including many atoms. Okay, so many atoms, but they still have that either positive charge or negative charge. Okay, it is not a neutral atom. Okay, so then we talk about acids and bases. Okay, so an acid and bases, you all run into acids and bases probably on a regular basis. And they give you this little chart, the pH value for different acids and bases, okay? And you can see on this chart, and I'll just read some of them out loud. Pure water has a pH of 7. Okay, that means that it is neutral. Anything that has a pH of 7 is uh, is considered neutral. It's not acidic and it's not basic. Okay, it's neutral. Anything with a number lower than that is acidic. Okay, so black coffee is a 5, orange juice is a 3 to 4, stomach acid is a 1, battery acid is a 0. Do not eat batteries. Bad idea. Okay, that acid will destroy your insides. Okay, and then bases have numbers more than 7. So seawater is an 8, baking soda is a 9, soapy water is a 12, bleach 13, drain cleaner is 14. Okay, so the pH tells you, that scale tells you how acidic or how toxic, how acidic or how basic a substance is. Okay, so that's very interesting. I always found that one a little bit interesting. Okay, and then the other thing is that there are different ways that a compound can form. That's the next thing he talks about in this chapter. How compounds form. Okay, chemical compounds. There's a chemical compound is formed or broken when a chemical reaction is happening. So if you have a chemical reaction, you have a compound either forming or breaking. Okay. And then he goes on to explain that there are two main goals of that make substances. Substances are motivated to react by two main goals. So substances want to react or have a reaction um, through these two main goals. Okay, and he goes on to explain those two main goals. One of them is when they want to transfer electrons between each other, the atoms. Okay, because they're not satisfied with the amount they have, so they're trading with each other. Okay, and then they become ionized because they're either positively charged now because they lost some electrons because the guy next door took them, or they're negatively charged because they have extra electrons because he stole them from this guy. Okay, so that's one way that they are motivated to react. And then a second way talks about polyatomic ions. And let's see. Okay, so the second goal is that they want really the ions and the atoms want to live in a world of electrical neutrality. So they don't want to have a bunch of positive atoms and a bunch of negative atoms. They all in the end want to be electrically neutral. So they all combine and transfer and everything so that they get that electrical neutrality, so that nobody's got extra electrons, nobody's got extra protons, we're all equal and neutral. Okay. All right. And then the last section of this chapter, he talks about chemical reactions, the reactions that take place after these two main goals were talked about, so the different chemical reactions are combustion, there's oxidation, there's redox, and precipitation. Okay, so those are all reactions. Oh, and sorry, an acid-base reaction. Okay, so acid-base, precipitation, redox, combustion, and oxidation. So those all are reactions that happen to chemicals, okay? And they gives you examples of those different ones. Of course, combustion is probably one of the easiest ones for us to understand. That's fire, okay? Oxidation is when rust is a result of oxidation. Redox always happens as a result of oxidation. So when one substance is oxidized, the other substance is redox, reduced, whatever that term is. Yeah, so it has that redox reaction when there's an oxide happening. Okay, and then the precipitation reaction, that is also explained. And that one, yeah. So when a compound comes out of a solution, it precipitates. After doing so, it is called a precipitate. Okay, so those are your different chemical reactions. Oh, and then I'm sorry, I keep forgetting this one, acid-base reaction. So that's there. Okay, when an acid and base react, the acid and base neutralize each other, and the products of the reaction are salt, water, and sometimes carbon dioxide. CO2, carbon dioxide. Yeah. Yeah, I think that's right. Okay. All right. So those are our different reactions. Okay. Moving on, chapter 12. Okay, chapter 12. Yes, this is where I feel more comfortable because this is the ones I did. Okay. Chapter 12. Great. We talked about wave, sound, and lights. Everybody remembers this one, right? All right. So we start out with the basic, what is a wave? Okay, we learned that a wave is, hold on one moment, please. Yes, okay. So a wave is when something propagates through time or space, okay? So waves are pretty much everywhere because light is composed of waves and there's pretty much always light. Okay, so it's, anyways, anything that's traveling or propagating through time or space, okay? And usually it requires a medium to travel through, such as water or air or what have you, but light does not require a medium to travel through. Light can travel through a vacuum, which has nothing in it, okay? I apologize. Let me restate. That's what I was going to check. So the actual definition of the wave, a disturbance in space and time that carries energy from one place to another. Okay? A disturbance in space and time that carries energy from one place to another. Okay? Which makes sense. That's the definition of the wave. Okay, and then of course we have our 3 common behaviors of waves that we talked about. Now there's, let's see, we have the 3 common behaviors of waves: reflection, refraction, and diffraction. Okay, and we talked definitely a good deal about that in class a couple months or 2 ago. So so you all should be pretty well familiar, but again, he has them all nice and described in here in case you need to refresh your memory. Reflection, refraction, and diffraction, the 3 behaviors of waves. Okay, now there are different types of waves. Okay, those are the behaviors of waves. Those are what waves do. Okay, there's 3 types of waves though. Okay, we have transverse waves. Okay, we have longitudinal waves, and we have circular waves. Okay, and I'll just briefly explain. So the transverse wave, of course, is when the direction of the disturbance, okay, and the direction of the wave are perpendicular. So if I have my hand, remember we did this little experiment in class. I have my hand oscillating up and down, okay, and it's causing a wave to go down this cord. Okay, so this is going up and down. This is going this way, back and forth. Okay, so those are perpendicular to one another. So that is a transverse wave. Okay, a longitudinal wave is a wave where the source of the wave, the disturbance, is oscillating in the same direction or parallel as the wave goes. Okay, so there, his example here was a loudspeaker. Okay, so when you have a loudspeaker, it's got this cone and everything in it that shakes back and forth like this. Okay, and as it does, it pushes the air molecules out this way, forming a wave, a sound wave, and that's what we hear. So this back and forth motion is going in the same direction as the wave going out. Okay, so this picture here is a good example. It's kind of hard to see there, but okay. So that was the longitudinal wave. And the last wave is the circular wave, okay, which is a little bit more difficult to grasp. But if you think about it with the floating object description that he gives, okay, that's there on page 255. Okay, so if you think about an object on the top of water, okay, and you have a wave coming up to that object floating on the water, okay, the wave is going to cause that object to first go up, okay, then as the wave comes down, the object is going to be coming down and around with it, okay, it's kind of hard to show you, but in the end, with the wave coming, it makes this circular motion, okay, you can kind of feel it if you're floating in a pool or something, you can kind of feel that whole up and down movement, okay, in the end, you're making actually a circular motion in one sense, okay? So that's the 3rd type of wave. Okay, and then of course he goes into talking about a little bit more about sound. We learned about echolocation, ultrasound, and sonar, all those types of things we touched on. The last thing I was going to touch on here is the Doppler effect. Okay, the Doppler effect is let's see here. Yes, so you have heard this effect yourself when the horn of an emergency vehicle or train has been sounding while the vehicle passed you by. Okay, so if you're sitting or standing on the street and a fire truck comes by, okay, you notice that there's a change in the pitch of the siren as it passes you by. Okay, it starts over here. It's probably going to be pretty high pitched. Okay, it comes, and as soon as it goes past you, it's going to start getting lower pitched. Okay, the pitch drops as the vehicle passes you. Okay, why is that? Well, that's because, as he illustrates in this little diagram, that's because the sound waves that that horn or siren is producing are coming to you when you're in front of the vehicle, when it's coming towards you. Okay, um, they're coming to you with a shorter wavelength and higher frequency. Okay, so as the train or the fire truck would approach you, the motion of the fire truck actually compresses the sound waves together so that they're closer together. Okay, so the frequency then coming into your ear is closer together. Okay, which makes a higher pitch. But then once the fire truck or train or whatever passes, it's not, you don't have that force pushing those sound waves anymore because it's past you. So any sound waves that are coming are just free flowing. Okay, so they're farther apart than when they're being forced in front of that engine. Okay, so they're free flowing now. So they're coming to you at a smaller frequency, lower frequency, which our ears pick up as a lower tone, so deeper sound. Okay, so that's again the Doppler effect. Okay. Uh, Moving on now, chapter 13. Yes, 13. Almost done. Okay. This was about electricity. We had the fancy, the cool looking lightning bolt there at the beginning of the chapter. All right. This one was pretty interesting, right? Okay, we talked about the two different ways that we experience electricity in our worlds, okay, on our human levels. Okay, we have static electricity is the first way we experience it, and we also have electrical current. Okay, so those are the two ways we can experience it. We've all known what static electricity is, right? And of course, electrical current is what's making this computer run at the moment. Okay, so we all know those different experiences. Um, in this chapter, he does explain about the lightning bolt, okay, and how the lightning bolt works. Um, some of it's kind of confusing, but generally, what we have to understand is that in a storm cloud, okay, there's a bunch of electrons because lightning is static electricity, okay. So there's a bunch of electrons gathering on the bottom of the storm cloud. Okay, and as those electrons are gathering on the bottom of the storm cloud, well, we have protons, because opposites attract, protons gathering on the surface of the ground. Okay, so those are attracting one another, right? Okay, so by the way, the motion of the ice crystals in the cloud is what causes the static buildup of those electrons on the bottom of the cloud. Okay, and then so of course we have the positive atoms there on the ground. Was I saying that right? Protons, positive, same thing. Okay, so then what happens is there's an electric field between the ground and the cloud. Okay, there's this high, like they need, you have electrons up here, you have protons down here. They're causing electrical field because they're attracted to each other. Okay, it's kind of like when you have two magnets and you can almost feel in between that there's like this force going on. Okay, it's kind of the same thing. You can't feel it as much, but sometimes you can almost feel a lightning storm in your body. It's kind of cool. Okay, so from the cloud we have something called leaders. Okay, they are channels of negative charges. They begin branching down through the air from the cloud to the ground. Okay, these leaders are composed of ionized air, a plasma that emits purple light, and a zapping or crackling sound. Okay, so we have those leaders coming down. Okay, and then when a branch of the leaders gets close to the ground, a channel of positive ions from the ground goes up, okay, called a streamer, and it begins to branch towards the leader, okay, and when they connect, it's called an attachment, and this all of this has happened in about a quarter of a second, they said, okay, so this is instant. That's why lightning is so fast. Okay, so now there is a whole channel all the way from the cloud to the ground, and the main return strike occurs and the mighty crack of lightning, okay? So one would think that the electrons in the cloud rush to the ground, since that is what lightning looks like. It looks like, in the sky, it looks like the lightning's coming to the ground. Well, in reality, it is, but the streamer is actually going up to it too. Okay, so they're connecting kind of. And what happens is that the proton, the positive ions are flowing up from the ground to the cloud. Okay, so that's really what's happening is this is coming down and this is coming up, and protons are streaming all the way up to the cloud. Okay, so it's kind of a yes and no scenario. Okay. All right, so then moving on, he talks about the electric current. Okay, so that was static electricity, lightning. Move on to the electric current. I have been talking for 45 minutes. Okay. The electric current, which is different types of electric currents are out there. We have the series and the parallel, right? The parallel networks are the ones that are combined by more than one resistor. I'm trying to find, here we go. Okay, so the parallel networks yes, so when a network is connected in parallel, the resistors are connected on their own branch or loop of the network, okay? And a electrical current that is connected in series, and a series network is produced on just one loop of wire, okay? The resistors are all placed on one loop of wire. And we saw this with our little light bulb lab that we did, turning on the light bulbs, connecting them all to one string of wire, and then some of them we connected each light bulb to their own string of wire, okay? And really the best thing I can say for this is just to look at the examples of yeah. Let me see here. Okay, so here we have series circuit, series network, and here's our parallel networks up here, okay? These two here. And of course, when there's only one resistor, series and parallel are the same. But if there's two or more resistors, they're either connected like this in parallel, or, like I said back here, they're connected like this in series. Okay? Okay, and then, so we have some three key elements of electricity here. We have voltage, we have current, and we have resistance, okay? So he briefly explains those different things. I think one thing that I was helping myself to understand all those things was voltage is the thing that pushes the current through the wire, and the resistors are what the current flows through. Okay, so the voltage is like somebody pushing you, and you are the current. You start running, and the resistor is a log on the road that you trip over, you fall and you keep going, okay? So it kind of stumbles you. Okay, that's what a resistor does to the current, and the voltage is what pushes the current through, okay? All right. So we move on to our last and final chapter, magnetism and electromagnetism. All right. So we learned about some different types of magnets. Okay, we know that some magnets are naturally found in the earth. Okay, some magnets can become some metals can become magnetized. Okay, um, let's see here. So the first thing we were talking about was kind of the nitty gritty of a magnet, of a magnetic material. We have in a magnetic material we have those little things called grains, and they kind of look like this microscopic shot here looks like there's little countries. Okay, there are a bunch of little countries. Those are all grains. Okay, and that's again, that's what's in a magnetic substance. And inside those grains are something called domains. Okay, they're kind of like the let me see where let's see domains. Yes. Okay. The interesting regions of aligned atoms are called domains. Okay, so they kind of align themselves in specific ways. Okay, in a domain. So and when you have different types of technology uses these domains to make to make their technology work. So their one example was when you have a recording head or a floppy disk or hard drive, and you need to store data on it. Okay, it explained that using the little recording head, the recording head basically lines up those domains in such a way that when the disk or the tape or whatever is read by the computer, it will recognize that data as a video or a movie or whatever it is that they recorded originally on there. Okay, so it just realigns those domains using magnetism. Okay, so magnetism is actually, which I didn't know, it's so very powerful in the technology world. Okay, and then we talked about these few fellows. We had that Hans Ørsted. Okay, Hans Ørsted here. He was the guy who originally figured out that there was a magnetic field around a current carrying wire. So, like our last lab where we had the battery attached to wire that went across that little compass, and when we attached the other end to the battery and made an electrical current, we saw that the compass needle moved because all of a sudden there was a magnetic field. Okay, so this Ørsted was the one who first discovered that. Okay, and Hans Andre Marie Ampere, he's the one who kind of put it to uh, an actual definition. Okay, so his definition was a current carrying wire produces a magnetic field around it, and the strength of the magnetic field is directly proportional to the current in the wire. Okay, so we kind of experimented with that again in our lab, that as the wire was moving farther away from that magnet, you could see, or from that compass, you could see the magnetic field down here was getting weaker and weaker. Okay, as you could tell that the compass needle wasn't moving as much after it was moved up the wire. Okay, so those two were the ones who figured that out. Okay, and then we moved on to this Faraday. Okay, Faraday's law of magnetic induction. Faraday figured out that when you have a coil of wire and you take a magnet and you pass that magnetic field through the wire, it'll actually create a little bit of electricity. Okay, so he kind of had the opposite of what Ørsted and Faraday and Ampere figured out. Okay, Ørsted and Ampere figured out that when there's an electrical current, there's a magnetic field. Faraday figured out when there's a magnetic field, you put it through wire, coil of wire, it'll produce an electric current. Okay, so it kind of works both ways. Okay, and then talked about a few other things in that chapter. Okay, great. So that is the end of that. So wow, that was just like a brief overview of the last half of the book. Okay, and again, pretty much in there contained all the answers that you will need to your exam. But again, the exam will be open book, so don't worry. You guys will do fine. Again, it's no big concern, and I'll be there and I'll help you if you need help, and I'll tell you on the day. If you need help, just raise your hand, and I will come over and we'll whisper and talk it out and everything as we go. Okay? So tell your parents to email me if you guys have any questions, but otherwise, I will see you on Tuesday.